So now we're going to continue with more problems, different line of ideas. So here I'm telling you a steel tensile coupon cut from 5 mm section is subject to tensile force as shown below. What is the axial strain in the narrow 20 mm wide section? So I'm giving you the width is 20, thickness is 5. So I give you the area. Here, this problem from a practice book that was relying on what you said, assuming the E. But it's because like some of the problems, the previous problem was from official FE practice. This is another practice book. So as a practice book, they may be slightly lousy of giving these numbers, but in the FE exam, they will give it to you. So basically, what is required here is to understand what is the strain. So if you look into this, your area is 20 times 500 millimeters square. Your sigma is P over A, which is 12,000 newtons over 100, so it's 120 megapascal. And your epsilon is sigma over E. So 120 over 200,000 gonna give you 6 times 10 to the power negative 4 over 600 micro epsilon. Micro is multiplied by 10 to the power 6. Divided by like a micro is 1 over 10 to the power 6 of the actual strain. So basically, even if you don't know the unit, if you use a work right, it starts with 6. So even if it's 6 times 10 to the power negative 4, it's like 600 micro, it's the same. Make sense? Any questions? Alright, so if we look here, here's the assumed E to be 2 times 10 to the power 11 pascals or 200 gigapascal, which is a classical assumption, by the way. It's supposed to be 200 gigapascal or 200,000 megapascal. Alright. Actually, we come now to a question which is supposed to be a follow-up with the previous question. This one. Steel tensile coupon cut 5 mm thick is subject to tensile force as shown below. What is the outer width? 20 mm dimension. Before you do anything, can someone tell me which ones will be the choices that make sense? Out of these 4 choices? Yes. B and D. Because this is tensile, so the 20 mm will reduce. So A and C doesn't make sense. You don't even need to worry about this. So it's B and D. That's why I'm telling you, even if you don't know the right answer, you may know the wrong answer. So now, without putting a single number yet, you knock down by your understanding to the main principle that A and C are impossible answers. It's B or D. Now let's do the calculations. And since this is a follow-up, leaving this is not a bad idea. So basically, also, this is another trashy part of this book. We use 0.3, typical is 0.3. So basically, epsilon lateral is 0.3 times 6 times 10 to the power negative 4. So it is 1.8 times 10 to the power negative 4. Your new width is 20 times 1 minus epsilon lateral. 1.8 times 10 to the power negative 4 will be equal 19.9964. Here, don't worry so much about the numbers they are not given to you, because this is just to illustrate what's going on. In a properly formatted question, this stuff will be provided to you. And over here, when they were answering the question, They started by the calculations of question 1, then they carried to question 2. And also, I don't think in the actual FE exam you will have this kind of sequential questions. This was just, I think it's a long question got broken into 2 pieces, but I don't feel this is the usual thing we're going to be dealing with. Any issues? Questions? All right. Anyone wants to copy? Next, for the beam shown below, what is the bending moment at point P? Well, it's definitely negative something. But now, you need to see what is the fastest possible way to get this done. Any suggestions? Yes?
Can we like solve for the reactions and then get the overall moment?
Yeah, you solve for the reactions and you either draw shear force diagram or take a section and say 30 multiplied by 3 minus this reaction multiplied by 2. This is one of the easiest ways. So if you do that, fine, this is your beam. You're gonna find that By is 34.5. This is 23.5, and this is 34.5, and this is 30. So the moment here, LB can be 30 times 3 minus 34 plus negative 34.5 times 2. 34.5 times 2 is 69. So negative 90 plus 69 is negative 21. Other ways, which is more rigorous, what was done in the solution. They got the reactions, they drew the shear force diagram, they accumulated the areas of the shear, but I wouldn't really do this unless you are looking for the maximum moment. So you need to actually draw the shear force diagram to verify where is the zero shears and get the maximum moment. But since we gave you the location, you can just do section equilibrium, obviously from the right side because it's easier. This is the easiest possible way to solve this question. But this doesn't mean it's the only way. I'm trying to save you time, but sometimes you need to do the whole thing. All right. Any questions? Issues? Here, section shown is used as a cross-section of a beam which has a maximum bending moment 256 kN, causing convexity on the bottom side. So it is a positive moment, producing tension on bottom, compression on top. What is the maximum bending stress in the beam? First of all, is this section symmetric? Wait, what do you think will happen to the centroid? Going up or going down? Gonna go up. So take question, answer A and C out. Because since the centroid is going up, this distance is higher, the sides in tension, the maximum stress is tension. So now you answer your question, 170 or 200. But you already took the compression out of the way by understanding what's going on here. So now your issue is still long, by the way, to get the centroid and to get the inertia and substitute the equation to see which of these two is the right one. Make sense? So if you are trying to solve this question, I'm not going to go through the whole details. you are supposed to divide it into 3 pieces. And if you got the centroid, it will be 125.4 millimeters from the bottom. And this distance is 120.6 millimeters. So this was a close call actually. Like you had also to verify this, but since the bottom area 150 by 50 is 7500 and 200 by 36 is 7200, but this is more spread, so it's a little bit further, it will pull it slightly up. Alright. Now, if you got the inertia, you're gonna go get I1 plus A1 T1 squared plus I2 A2 T2 squared, the moment is going like this by the way, plus I3 plus A3 T3 squared. When you do these calculations and do everything, you find it's 400 megapascal inside. So this problem is a bit long because you actually need to solve it. But even if you are not sure, if you know it's inside, you are between 170 and 200. And unfortunately, this is a silly problem because the numbers are close to each other. So you can't really eyeball it that much. You were fortunate enough to figure out that it's probably tension, but this is where your luck ends. Now you have to calculate or to do the calculations. And if you look at the calculations, here it is. This is on the longer side of problems, because this needs some amount of work. Any questions? Issues? Correct. Another more circuit problem. This is flow drawing because you have other 200s here and there. This is just like a sketch. For the state of stress shown below, all stress in megapascal, what is the maximum compression normal stress? This is basically asking for sigma minimum. Because since you have 200 compression and 400 tension, this means that sigma maximum is tension and sigma minimum is compression. So now we are asking for actual sigma minimum. So now you need either to draw more circle or to use the equation to figure this one out. So if you are drawing more circle, you have negative 200 and this will be counterclockwise, so it's negative 100 and this is 400 and positive 100. So this center is the average 400 minus 200 over 2, so this is positive 100. And your R, the square root of 100 squared plus 300 squared, which will be 316. So sigma minimum equals sigma average minus R, 100 minus 316 equal negative 260, which is answer A. Actually, this is a bit bad because C is the maximum tension. It's 100 plus 316. And here they also should be more specific. This is the magnitude of the maximum compression, because here they didn't include signs. Any questions? Issues? I simply plotted these 2 points and got the location of the center, then got the radius from this triangle, the hypotenuse, then I said sigma average minus R is sigma minimum, sigma average plus R is sigma maximum. The other alternative is use this equation. Up to you.
All right. After a couple of questions that are a bit silly, let's give you something that is on the better side of things. Any questions so far?
Here, for the beam loaded shown below, what is the correction for the building load diagram?
I will answer this. Yes, sir.
I think it would be the second one, just because I noticed like be a straight line like a triangle, and then curves, and then goes back to straight line and triangle.
Yes, well, the edges is the answer. This is concentrated load by the distance between a straight line and a straight line, not a constant line, not a curve, not two curves. So it's the second one. So this is more like the things in the magazines when you're kids. Yes.
No, that was supposed to.
Yeah. So basically, this is more like the things when you were kids and you're putting like small things which switch. So this is basically relying on your understanding that the bending moment from concentrated load supposed to be straight inclined, like inclined straight line, and the moment from the parabola to the curve. So they didn't mess with you in the middle part. You just play on the edges. This is possible. Like this is one possibility is to test you in your expectation of the shape of the moment, bending moment diagram. Any issues? And this is basically explaining this, so you don't really need to worry about it. The results of an inside test of a prismatic metal specimen are summarized in the curves below. What is the most nearly modulus of elasticity of the specimen? Thoughts? The modulus of elasticity is the slope of the linear part. However, here it's not very easy to deduce it, so you may need to draw a tangent. If you draw a tangent, you find that you're intersecting somewhere here. 370, 380. Over 0.002 will give you 190. So this is more of a visual inspection kind of question. This is a little bit rough because it's more subjective. However, the answers they are giving are not very close to each other. So it allows you to some room of mistake because they tell you what is the most nearly. So they already protected themselves from the fact that you may not get this number. You just need something near. And here's the answer. Drawing a tangent to the beginning of the curve, it intersected at 380. So 380 is 0.002, so it's 190. Give or take a 5. Any questions? Issues? All right. Okay. Now comes a bit of a fun question. Generalized Hooke's law. For the 3D steel element shown below, assume that all loads are uniformly distributed on the basis of the element. What is the deformed length in Z direction? What's happening here? I'm tensioning in Z direction. I'm tensioning in X direction, which will reduce Z a bit. I'm compressing in Y direction, which will increase Z a bit. So what is your expectation? Z will increase or decrease in total? Increase, so peace out. So now you are between A and C and D. Let's do the calculation. This is generalized Hooke's law. You get sigma X, you get sigma Y, you get sigma Z. You are supposed to be given mu, obviously. So here you, but since I'm telling you this book was a little bit lousy on this, because it's a practice book, mu will be 0.3. And E for the steel will be 200 gigapascal. So, let's do this. So sigma X is 1300 times 1000 megnewtons over what is it? 75 by 60 equal positive 289 megapascal. Sigma y equal negative 1500 times 1000 megnewtons. The area in this phase is 75 by 120, which would be negative 167 megapascal. Sigma z will be 1800 tension, so it's positive 1800 times 1000 over 120 by 60 equal positive 250 megapascal. What I'm trying to get? I'm trying to get epsilon z, which will be sigma z over E minus nu sigma x over E minus nu sigma y over E. Be mindful to your signs. 1 over E, 1 over 200,000 megapascals will be sigma z 250 minus nu times sigma x 0.3 times 289 minus 0.3 times negative 167, which will give you the strain 1.067 times 10 to the power negative 7. The new length is positive, so we were correct. We will increase in length. L dash equals 75 1 plus epsilon, which will be 75.08 millimeters. So the answer is actually C. This is a bit tedious, but it's just being careful with your numbers. Yes.
Could you maybe go over the sign convention of the strain?
The sign convention of the strain is like the sign convention of the stress. If compression produces a negative stress, produces negative strain. So if something is compressed, it's decreasing in length. Tension is positive stress producing positive strain, increasing the length. So here, when you substitute here, if you get a positive epsilon, this means that this thing is elongating and it's under tension in general, in total, because you have the effect of the direction and the interaction of the other two directions. If the sign is negative, this means it's compressed and the length is decreasing. So this is L node 1 plus nu, whatever nu is positive or negative. So if it's negative, it's positive, negative, then the length is decreasing. If it's positive, 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 it's increasing. So basically the sign convention is the following. Tension, positive sigma, positive epsilon, increasing length. Compression, negative sigma, negative epsilon, decreasing length. Make sense? All right.
So I thought X was in tension.
Well, X is tension. No, but the thing, when X is in tension, it is decreasing the opposite directions. Because if it's elongating in X, it's decreasing in Y and Z. And if it's compressed in Y, it's bulging in the other directions. So that's why this formula is a little bit confusing, and that's why I have to be careful. Because the direct effect is what I explained here. While when you are talking about nu, it reverses. Tension in a direction, since the volume is constant, have to decrease the other two directions. Compression in a direction, have to increase the dimension in the other two directions. Make sense? All right. Anyone still copy? Okay. A steel pipe having outer diameter 100 millimeter and wall thickness 5 millimeter carries a water pressure of 300 kilopascal. What is the circumferential stress in the pipe?
circumferential stress or tangential stress, all of this hoop stress. The other one is longitudinal. The names can be a little bit annoying, but it's more or less the same thing. The circumference or the perimeter of the pipe is the hoop stress, the other direction is the longitudinal stress, depending if the person writing the question like basketball or not. Thoughts. Here, T inner equal 100 minus 2T, so it's equal 90 millimeter. Main radius or average equal 50 plus 45 over 2 equal 47.5. I don't know why you are insisting on this while you are teaching it in strength. The thing is depending how big is the radius compared to the thickness. So if it's a very large thing, the inner radius will suffice. If it's fairly small, the mean radius will be more accurate in this case. So, according to what we know, which is called thin wall theory, sigma equal PR over T, which is 300 megapascal, 300.3 megapascal times R, which is 47.5 over T, which is 5, equal 2.85 megapascal. I divided this by 1,000 to transfer it from kilopascal to megapascal. 1 megapascal is 1,000 kilopascals, which means that the answer is T. As a matter of fact, this book was silly enough that way later on in these questions will give you the same problem, but will ask you to solve it rigorously, which is not something you're going to take with an AP exam. But I will just show you how accurate this is thing. So here, based on same wall theory, which is hoop, even here it's called hoop stress, although it's asked for circumferential stress. So here for here it's called hoop stress. The answer is D. Okay. Any issues so far? I know this is bringing a lot of memories, maybe good, maybe bad. At least you remember them. The moment you remember them is what matters. Your personal opinion about them is a different issue. A steel beam is loaded with 2-point loads as shown. What is the deflection at the midspan? Position. Actually, you have two cases that the load is known in the middle and you want the middle span, so for both cases you're going to use the equation of the elastic curve. And the total span is 7 meters. So you're going to substitute 3.5 meters for this case, then 3.5 meters for that case, get the deflection for both added up. Here, there is no real art here. You are just opening the superposition table, doing the job, doing the calculations, and you will find that your deflection is 40 millimeters. EI is given to you. You have everything you need. All you need to do is to apply the equation of a simple beam under a load, not in the middle twice. One time get me here, one time get me here, and the loads are not equal, the spans are not equal, so don't dream of using symmetry. You can't get one multiplied by 2, you have to do twice actually. I'm not going to waste time on this with just substitution, but if you do, you find the answer is 39.8, which is practically 40. And here's the equation of the elastic curve. This is a silly one because you have to do it twice using the equation of the elastic curve, so this is not very user-friendly. Any issues? Questions? All right. More with superposition problems. A simply supported beam is loaded with a couple at the line support as shown. What is the maximum deflection? This is actually way easier than the previous one. Go to the table. For this case, use the Y maximum, substitute your moment is 50 Newton per meter or 50,000 Newton meter because EI is 6 to the power 6 Newton per meter square. The only issue here is that the units are not consistent. So you have to be mindful to that. If you do this, you find your maximum deflection is 19. And these numbers are really bad because it's 17, 19, 21, 23, and good luck with guessing this. If you can actually guess the maximum deflection for a single beam out with a couple at the side by just looking to it, then probably you are doing black magic. This is not something you can know on the top of your head, you know, especially with this kind of numbers. Like the difference is like within like what? 20%? Any questions? Issues? If you go to your table, you find Y maximum negative m naught L square over 243 EI. You substitute, you get negative 0.0192 meter or negative 19.2 millimeter. Here we told you the maximum deflection is a magnitude. We didn't get you into the issue of positive or negative. Any questions? Issues? Questions? Because straightforward is a little bit depending on who's thinking. I see this straightforward question because you're going to take the table and do calculations. For you, since you hate the calculations, may not be that straightforward. Straightforward for you when you know the calculations is easy. A hollow steel shaft outside the air diameter 20 millimeter, outside diameter 30 millimeter is subjected to a torsional moment 200 Newton meter. If the length of the shaft is 50 centimeter, what is the twist angle? This is as straightforward as it gets. Phi equal TL over JG. Of course here, G have to be 80,000 gigapascal, but this is something have to be 80 gigapascal or 80,000 megapascal, this has to be given to you. Assuming that you know G, this question is simply telling you this. Phi equal TL over JG. T is 200 Newton meter or 200,000 Newton millimeter. L is 50 centimeters or 500 millimeter. G is 80 times 10 to the power 3 megapascal. J. What is J for a hollow pipe? What is J for a pipe? For a circular section, pi over 2 c to the power 4. So this is pi over 2 c outer, which is 15 to the power 4 minus 10 to the power 4. Any hollow section is outer minus inner, whatever the property is.
Is there any class in here right now?
We don't know. It's supposed to be 4 to 7.
Oh, it's supposed to be in a different room?
I don't know. Is it,
Thanks, Registrar.
is it stated to be here?
Hmm?
Is it stated to be in this room?
We were supposed to be in here, but I guess the registrar goofed out. That's
Well,
fine.
This is
We'll find
FE
someone.
this is FE review session, so I don't. This is supposedly this is booked every week at this time. So, but I'm the first one, so I'm not really sure. So if you find another room, this is great. If not, we can figure something out.
Okay, sure. All right, thank you.
All right. So if you do all of this, you will find that your angle 0.0196 radians. This doesn't look like anything here because this is degrees. So if you multiply this by 180 over pi, you're gonna get it to be 1.12 degrees. Right? Hopefully you're up here. Let's see. Not the first time to come to. Actually, last fall, they scheduled 2 final exams in the same room. One was makeup first class, one was for another class in civil engineering. But we reserved the room first, so they had to get another. Plus, we came to first.
All right. Any issues so far? Getting J, phi T N over GJ, we're good. The section shown is used as a cross-section beam that have a maximum shear force V equal 50 kN. All dimensions are in millimeter. What is the maximum shear stress in the beam? How to get it? Where will it happen? All valid questions. How many of you took steel design? Can you help me to get this thing really fast? Like really fast, like. I don't teach steel, but I studied steel before, and I know that in T I sections, the shear is happening at the middle, and you can see that T max, tau maximum equal V over area web. I know this very well. So this is 50,000 over 160 by 20, which is equal for 15.6 megapascal. So the answer is 15, which is answer D. However, if you decide to do it accurately, the answer is 14.7, and the approximate one is 15.6. The difference is 6% error. So in this case, the approximation that the tau maximum equal E A V over A web is totally valid. And that's why I asked to propose it to steel. As a matter of fact, I explained this in strength materials, but there is no way in hell anyone remembers it. That's why I go to steel, where you actually deal with this. I'm trying not to really pick on you by telling you something I said in 3 minutes in a strength class. I'm referring to more reasonable reference. And the case will continue. Right. Any issues so far? Questions? Let's see another question. At a particular point on a beam subjected to transverse loads, the following stresses have been measured. Bending stress 28.5 KSI tension, sigma y0, tau xy 14.8 KSI. They still have this sigma ultimate values, 45 KSI tension, tau ultimate 30 KSI. The factor of safety based on stress is most likely what? This is a combined loading problem cut into half. We give you sigma, we give you sigma y, we give you tau, we give you the ultimates. So basically you are supposed to draw more circle with the equations to get tau maximum and sigma maximum, sigma ultimate over sigma maximum will be factor of safety for sigma, tau ultimate over tau maximum will be sigma factor of safety for tau, gives us 1. As I told you, this can happen, but the problem is already truncated. So here we already finished half the problem. It's getting the stresses. We're just giving you stresses that you need to get tau maximum and sigma maximum and compare. So, if you go draw some sort of a more circle, the size wouldn't matter because just need the size. You have 0 and 14.8, and you have 28.5 and say negative 14.8. If you join these, you will find that this is 14.25. And your radius is 14.25 square plus 14.8 square, which will be 20.6, which means that sigma maximum equal average 14.25 plus 20.6 equals 34.85, and tau maximum equal R equal 20.6. Factor of safety for tau will be equal 30 over 20.6, which is 1.46. One of your choices, but this is risky because it calculates other one yet. Don't rush here. Be careful. Factor of safety for sigma is equal 45 over 34.85 equal 1.29, and that's your answer. C. This is really mean because one of the two factors of safety is one of the answers. So if you are really rushing it, you may do this mistake easy. So be careful. Since you are calculating more than one factor of safety, wait till you get them to say, pick the name. And here is a problem solution. Any questions? Issues? I'm closer to finish than the beginning, so don't worry. A steel rod of diameter 20 millimeter is fixed at the left end as shown at temperature of 20 C. A gap of 0.1 millimeter exists between the right end and the rod and the rest wall. If the temperature of the rod is raised to 120 C, so this is 100, what is the stress in the rod? Actually, they saved you big amount of speculation because there is no answer of zero, which means that the gap will close. Now the question, how much it will close? If there was a zero, now you first have to check for free thermal expansion and see if that free expansion is less than 0.1 or not. They eliminate this possibility because there is no zero. It seems that in this question, people putting a free exam are less equal than us in instance of materials, because we played this prank several times, and they get people every time. All right. So if you are calculating L alpha delta T, they are supposed to give you alpha. Obviously, they don't have it here in the problem statement. Alpha will be 11.7 times 10 to the power negative 6. This will happen. This will not happen in an FE exam. 0.152 millimeter. So you already know that this gap will close. All right, great. So there is different ways of doing this, but you can say that delta equal alpha L delta T plus PL over AE, and this is your sigma. Solve L is 130. E is 200 times 10 to the power 3 to make it megapascal. Substitute with this is 0.1 millimeter. You're gonna get sigma equal negative 79.9 megapascal. So your answer is actually C. The stress is 80 megapascal. When they were doing this in the solution, they chased their tail a little bit, but this is more saving you time. And also you will see the stress at the length is 130.1 millimeter, which wouldn't matter at all. Since the answer is in the order of 20, 40, 80, 160, this wouldn't really matter. Don't really get caught with these small things. You are not like doing like a PhD here, like you are just solving a problem with approximated numbers. Any problems so far? Issues? Alright. Same problem we said before. A steel pipe having 100 millimeter outer diameter, wall thickness 5 millimeter, carries motor pressure 100 kilopascal. What is the circumferential stress in the pipe using the Sick-Ward theory? As a matter of fact, since we don't teach this in strength of materials, I took the effort and Googled what is the Sick-Ward theory because we don't teach it, and I found out that, okay, they have the solution, but I'm not supposed to explain something that I don't really know. It was found that actually, after like a tedious derivation, that sigma hoop equal P internal R outer square plus R inner square over R outer square minus R inner square. This is basically it. So this is 300, this is 0.3 megapascal. R outer is 50, our inner is 45, which will give you 2.86 megapascal.
Can you show it?
I'm sorry, so sorry. Sigma hoop equal P internal, our outer square plus our inner square, or our outer square minus our inner square, you substitute get 2.86. So the answer is still 2.85. And actually, the difference is 0.35% error. That's why no one uses nonsense unless there is something really critical here. So see, to some point they were telling you this is silly, but we just wanted to prove it to you. This wouldn't be the case in the exam. But I just found it worth mentioning. Any questions so far? Issues? No, I have to read like 3 pages of derivation to reach this equation. But at least now I know where it comes from, and now you also know that this is like, doesn't really matter. This is like the same issue with engineering stress and engineering strain. Are you updating the area and the limits when your attention is the center or not? Same exact thing. Or using the actual angle or small angle approximations. All of this stuff doesn't really matter. And this is one proof of it. Any issues so far? Questions? Alright. Let's talk about something more serious. This sounds really scary, but really doesn't. A block of elastic material is used to support vertical load to 200 kN, shown below. The left face of the block is fused to a rigid surface. So basically, we are having this same attached to a wall. While the load piece is evenly over the right face as shown. The elastic properties of the material are modulus of elasticity, 4 gigapascal, who assumes the ratio 0.28. What is the minimum values of the dimensions A and B if the maximum allowable shear stress is 30 megapascal and the maximum downward deflection of the loaded face is 1 millimeter? Here, you have 2 criterions to satisfy: shear stress, shear strain. Do you have G? You don't. You have E and have mu. Use the formula to get G from E and U. Then start working. This problem is not very hard. It just took a ton of text to explain. But it's not hard at all, really. It just also rely on your sketching things. So, let's see what we have here. First of all, G equal E over 2, 1 plus nu. So it's equal 4 over 2, 1 plus 0.28 equal 1.56 gigapascal. Now, tau equal P over A. Tau is supposed to be 30 megapascal. P is 200,000 newtons. What is the area? What is my area? What is the area under shear from this sketch? 80 times B, correct. So this is 80 times B. Give you B equal 84 millimeter. Which means that you are between choice C and D. Because B have to be at least 84. So 85 is fine. 70 is not fine. Plus you need the nearest anyway. So now you solve with half the issue. Where is the other half? The other half coming that this thing which is 84 by A and you don't know A yet will do like this and the gamma will produce. This G tau equal G gamma. Tau equal 30. G equal 1.56. What is gamma equal to? Gamma is equal delta over A. What is the delta we told you? We told the deflection can exceed 1 millimeter. So this is 1. Solve for A. A have to be 55 millimeters. This is the nearest answer. So this is what satisfies those criteria. So this problem is tedious to understand and draw, but calculation-wise, the equations are not hard. But shear problems with this kind of planes is usually tricky because it's a 3D problem and you need to really understand which is which. All right. Another one. A 20 feet beam carries a load that increases linearly from a maximum of 400 pound-feet at left to 0 pound-feet at the midspan of the beam. Measure from the left support. The point at which the shear is 0 is most nearly what? What do you need to do here? This load is 200 to 400 multiplied by 10 multiplied by half, concentrated at one third of this, which is at 3.33 here. You can calculate the reactions. And when you calculate the reactions, equate this reaction with the area of trapezium that you don't know yet, and get distance. So this is basically a geometry problem. If you do so, you get 5.9. Which, by the way, makes sense because this is more loaded this way. So 14.1 can be the answer. It's one of these three. You are expecting this to become equal to the reaction more than half of this half, which is before 10 feet. If you look to the calculations, it's a little bit hard and they try to do it with integration. I don't find this necessary. You could just solve it as a geometry problem. Any questions? Issues? All right. Anyone still copying? A symmetric R-shaped section shown below the left has a property Ix 540 inches more for 826 inch square. The section is then reinforced with a rectangular plate 8 inch wide, 1 inch thick as shown in the right. What is the percentage increase in centroidal moment of inertia of the section as a result of any of the plate? Basically, you need to get the new centroid, which will be related down. You have this inertia just multiplied by the distance, which will be A by D squared. Then get the inertia of this plate, add it to the inertia of the I after being transformed, divide this by this, you find the increase 67%. This is one of the things you do when you are out of options. Sticking a plate to the edge of an I-beam significantly improves its performance. Because you are adding area way far from the centroid, so this already adds much more to the inertia. Because the AT square is massive. As I told you, I'm not gonna explain a lot about the calculations. You can see it here, but that's basically it. Any issues so far? Questions? So now I'm waiting for your questions if you have any. And this basically is the third and last part of the class. So now if you have any questions related to anything that I've explained or anything in extrinsic materials, generally you need to know, it's a good time. Any questions? Going once, going twice. Good luck with your exam.